much for introducing. And at first, I appreciate organizers for giving this opportunity. So, in today's talk, I want to focus on these fundamental groups of two-one factors. So, this is a well-known invariant for two-one factors, and this notion is classical and first introduced by Murray and von Neumann. They computed the fundamental group of the hyperfinite two-one factor, and then asked the general behavior, what happened in the general situation. But, well, in general, to study this fundamental group is very difficult, and technically very difficult. So, until recently, very few numbers of computations are done in the two-one factor theory. So, but as in Sorin's talk today, Sorin Prof introduced a new technology to study this fundamental group. This is in the 2001. Then he particularly provided a lot of new computation for two-one factors. So the techniques used in this context is now so-called intertwining argument by bimodules, and the development done by this technique is now so-called deformation rigidity theory. This is exactly Sorin introduced in today's lecture. So in today's talk, using this technical development by the deformation rigidity theory, I particularly want to study fundamental groups of the tensor product two-one factors. This is my aim today. Okay, so in this talk, I first record the notion of these fundamental groups, and also I want to mention the history of this for computation of these fundamental groups. Okay, so record that. Okay. Our setting is M is always two-one factor, but always separable period. Sorry, separable. And tau is a trace, unique trace. So at first, record that amplification for any positive real number t, you can define t to the power of m. This is called amplification. Is defined by if t is between 0 and 1, you can simply put P and P. Here P is a projection such that the trace value coincides with T. Well, M is a two-one factor, so you can always find such a projection P, right? But well, in general, this P is not unique, so you can also have another projection Q. But Q also takes a value at T. But well, because this is a two-one factor, P and Q are equivalent in the von Neumann universe. So finally, it turns out that PMP and QMQ are isomorphic. So this is defined up to star isomorphism, right? And in the general situation, okay, so in the general situation, T is larger than 1, but the same happens for just positive T. The same definition can be given. You can put P and P tensor matrix algebra. Here, n is a natural number which satisfies this condition. N is rather than t, and P is a projection again, such that the projection value coincides with t over n. This is between 0 and 1, so that you can define this object. In that case, still you can prove the well-definedness of this object. This does not depend on the choice of n or something t or something else. But this is an easy exercise, so that you can prove this amplification, right? So this is well. But why do we use this kind of a tensor product? The one advantage of using this notion is that we have we always have this kind of natural isomorphism. Well, this is both sides is determined up to psi isomorphic. So by choosing appropriate, representative, you can assume that this is really equivalent, the same object. Right? Now you can define the fundamental group. The fundamental group of this 2-1 factor m is defined as positive number t such that this amplification by t and m. You have two 2-1 factors, but they are isomorphic as a von Neumann algebra. So this is the star isomorphism. But this is the definition. So at first, it's easy to check that this is really a group, and it is subgroup of this multiplicative group of positive real numbers. This is subgroup because of the first equation holds, right? It's very easy. So this is an invariant on 2-1 factor which take values at the subgroup of R plus star. Okay. So Marian and von Neumann computed this fundamental group of the hyperfinite 2-1 factor coincides with R plus star itself. And then ask the general behavior. So what happened for any other, other m. But in general, to compute this group is very, very difficult. Technically very difficult. Why? Because you have to compute this f of n, you have to distinguish t power of n and n, right? But in general, in the 2-1 factor series or von Neumann algebra series, the most difficult question is to distinguish two given factors, right? So in general, the most easy way of doing so is one is amenable, the other is non-amenable, so that they are non-isomorphic or something like that. But this kind of strategy cannot be used for this context because t power of n and n almost have the same property in the abstract sense. If m has nice property, then t power of m also have such a nice property, so that it's very difficult to distinguish two 2-1 factors, right? This is a technical difficulty of computation for the fundamental groups. So today we want to consider the question raised by Marian and von Neumann. That means what happened in the general situation. But later, I don't know but later this question by Marian von Neumann is formulated as follows. If we put S of factor is okay, you define this subset, family of subgroups of R plus R, which is realized as a some fundamental group of a 2-1 factor. Then find a nice characterization of this class. Good characterization. Of this class. This is a natural question. So today we want to consider this question. This is the first question, but this is a very, very difficult question. The terminology is good means it's a definition we need a notion of 2-1 factor. So what good is the best answer to this question is to find some characterization which do not use the 2-1 factor technology, only in terms of some R or R plus or something like. This is the final goal, but it's highly non-trivial. Anyway, this is the question, and so next I want to consider what is known. What is known for this class. So a general property, the following is well known. For any element G of this SO factor, there exists Polish group and homomorphism, continuous homomorphism on this G. This is a well known. This is a kind of weak property, very general things, but still this gives us information. For example, such a G must be a Borel subset of R plus star. Right? You need some restriction. So this has some very weak information for this class SO factor. Right? But this is a very general thing, and the proof is not very difficult. If you have only to put for M21 factor M, this is actually very crucial. And automorphism group of M tensor B over H on the subject, this subject onto the fundamental groups. This is so-called the model map, because this is a trinity part. This admits a unique choice up to scalars. So by composing the automorphism with such a unique choice, you have some scalar. You can pick up such a scalar multiple. So this is a model map. But I omit this part. This is not difficult. You can prove this by yourself. This is a general property. So next we see the concrete examples of this class. This class SO factor contains the following items. The first is by Mare and von Neumann, the first one. This R plus star itself. This is because hyperfinite one factor satisfies this, right? This is 1942, the first work. And the second work is by Alan Kohn, 1980. He proved that some countable groups subgroups inside R plus star must be contained in this S class, the class S factor. Why? He used notion of so-called property T of discrete groups. He used okay. So whenever you take the ICC property T discrete groups, then the corresponding group to one factor always satisfies this condition. I mean, fundamental group is countable. He uses the so-called countability versus uncountability argument. So this is just not the complete computation, but a kind of existence result. But still, this is interesting because this is the first result of the class of SO factor, which is not equal to R plus star, right? And also the use of the property T in the von Neumann algebra context is also, I mean, very interesting. So next work is by Sorin Popper. He proved that actually any countable subgroup in R plus star is actually contained in this class. For any given two factor, any given countable subgroup for R plus star, he constructed a concrete two-one factor whose fundamental group equal to the prescribed countable subgroup. Right? So this is exactly the Sorin's new technology, new discovery. So,
sorry. So just to be clear, this means the cyclic group generated by any element of R is allowed.
Yeah. Any.
Any. Not just cyclic operation.
This is Sorin, and the text is Sorin's new discovery. Actually, after this Popper's work, there's several numbers of computation, by several authors. But among other things, I'm sorry, but today I'm only interested in the class S or factor. For this thing, the next research is by Popper. They provided some many uncountable subgroups is contained in this class. So, well, in that world, people only discuss the countable things, but Popper succeeded to prove the existence of uncountable things, which is not equal to R plus star itself. This is very interesting. Well, but proof uses so-called Bell category argument. So this is an existence result. But well, the terminology many is very difficult to explain. But they actually they discovered some connection between the fundamental group of some specific to one factor with some invariant from the ergodic theory. So by controlling the ergodic theory side, you can provide some such examples. Okay. Now, so thanks to such a technical development, we know a lot of such examples. I mean, we know a lot of examples are contained in the class S of factor. And the final two things are, given in the framework of the deformation rigidity theory. Okay, and my work today is also based on this the final two things, the deformation rigidity theory. I will use these technologies to study this tensor plus one factors. Okay, and in my knowledge, this general property, and these examples, they are all information we know so far. I mean, with respect to the class S of factor. And one remark is that, okay, this is not related to the class S of factor, but it's worth mentioning that in the free probability theory, also some examples are given. The free group of infinite generators, this is free group factors, the fundamental group coincides with R plus star. And also, the computing this fundamental group, the fundamental group of the free groups with finitely many generators. This is equivalent to the classification problem. Well, this one is well-known the free group factor problem. But unfortunately, well, to solve this problem, you have only to compute this invariant. But so far, there is no way of computing. Unfortunately. Okay, so the first one is proved by Radresk and Voigt-Resk, and the second one is in my knowledge, Voigt-Resk and Daikuma. Okay. Now I stop the introduction part. Okay, we are interested in the class S of factor, and particularly today we are particularly interested in the behavior of the tensor product situation. So, okay, the tensor product case. So, to consider this situation, let's fix n and n. There are two factors. Okay. At first, I want to look at the following some elementary, equation. Okay. You always have this equation. This is up to side homomorphism also. But well, what is this? This is amplification and this is amplification. The tensor product. This coincides with the amplification of the tensor product. It's but actually it's very easy because in the definition of the amplification, you can always find your projection from your favorite place. You can, for example, take from M or N or something like. Very easy equation. But this simple equation gives the following some observations. One is if you put S equal 1 over t, then if you assume that S is 1 over t, you have this isomorphic, right? Well, this is somehow trivial, but this is important in our work because when you are interested in the structure of tensor product here, then this is always the same as this decomposition up to non-canonical isomorphic. But this means to consider the tensor component M is the same as considering the tensor component T star of M. You cannot distinguish two things. This is one observation. And next observation is if you assume that T is from the fundamental group of N, S is from N, then you have this, right? The first one is from the definition of T and S, right? And the second one is that one. So you have the left hand side, right hand side coincide. That means TS is contained in the fundamental group of M design. So you conclude times we always have this inclusion for the tensor product and the fundamental groups, right? So a natural question here is, how about the converse inclusion? Well, this is a very natural question because if the converse happens, then this is the equality. But if this is equality, it's a very useful formula to compute the fundamental groups, right? If you are interested in computing the fundamental group of the tensor product to one factor, you have only to compute the fundamental group of each tensor component. It is kind of a reduction method from the tensor product to the tensor component, right? So we won't study when this happens. This is a question too. Well, but again, in general, it's very difficult question to study. I don't know any counterexample for these things, but thanks to the technical development in the deformation rigidity theory, Ozawa and Popper provided first positive answer to this question. It's a positive answer, but this is a first result. This is so-called prime factorization. So the theorem they prove that assume that M1, M2, there are some of free group factors but more generally so-called hyperbolic groups or bi-exact groups or something like that. There is some abstract characterization. And N1, N2, there are any two factors. Then assume that your tensor product is the same as the other tensor product. For simplicity, I name it M. Okay, you are interested in free group factors, right? And the other is arbitrary. So you are interested in the tensor product of two two-one factors. But assume that this your tensor product has abstract decomposition with N. Then what happens? So the conclusion is, well, okay. The conclusion is, then there exists positive real number T with some decomposition as I mentioned, you always have this kind of isomorphism, but this is non-canonical isomorphism. That means there is T with a fixed isomorphism, and there is U, unitary element of M, such that U M1T, this guy. U sir, this left hand side is, oh sorry, equal, is exactly N1. And the other guy, M2, 1 over T, is exactly N2. Actually, or some opposite phenomena. There always is the possibility of other index, right? This is the conclusion. This is not good. Yes. This is the conclusion. Well, this is very obviously very strong theorem. That means, okay, you are free group factor M1 and M2. If this has an abstract tensor decomposition N1 tensor N2, then this must coincide with a kind of trivial perturbation of your given M1, M2, right? As I mentioned, okay, so this is a kind of possibility always happens, and this this is just a unitary conjugacy inside the N. This doesn't change any information, right? So unitary conjugacy, this is a trivial isomorphic. You can essentially remove this U, then up to this identification, you can conclude that your N1 and N2 is actually coming from some some perturbation of the ordinary decomposition, right? That means the tensor product of M1 tensor N2, M2 only has a unique tensor decomposition. That is so-called the unique prime factorization phenomenon for free group factors. Okay, so now an immediate corollary is, thanks to this strong theorem, immediate conclusion is that conjecture to hold. Yes, for free group factors. More general by exact group factors, right? That means if you put both M and N as free group factors, you always have this equation. This is a simple consequence from the main theorem. From the main theorem, from the theorem to the corollary is very easy. So now this is the first example, first positive answer given in the framework, this question 2. And also thanks to the technical development of Ozawa and Papa, the further examples are given in our deformation rigidity theory, but I omit other examples there.
But what you're saying is kind of vacuous because of course you don't know what the fundamental group is, right? And so if it is R, then it's not saying
That's right. The free group factor is not a good example in that sense. Anyway. So, well, okay. So, okay, this is our problem today. So I suggest another approach to this problem question too. So we consider the following property. The following P of at 1 factor n. Okay, today we name it the conditional star. We have this equality for any to 1 factor. This is a property. We want to consider this as a property of M satisfies this condition. If M satisfies this positive answer to the question 2 for any to 1 factor n. This is obviously a slightly different viewpoint from the one order propagate. So, and the main theorem today is there are such examples, and also some corollaries. And actually, corollary part is the main observation today. So, the first main theorem today, actually, the only main theorem today, by myself. The following M satisfies that condition. First one is free group factors, but more generally, by that something like. But I don't want to explain this part. Just the fundamental example is this. Oh, sorry, A. The free product of a factor, and each one is diffuse and treasure. Okay, and the final one is the cross product, but this is so-called Bernoulli fraction. So they are examples, but well, this is the main theorem, but not the main observation. The main observation is that I have two corollaries. The first corollary is that for any this class G from S of factor, then by definition you can always find some 2-1 factor M such that the fundamental group coincides with G. But actually there exists M 2-1 factor with our condition star such that the fundamental group coincides with G. This is one corollary. And the second corollary is using this first corollary A, you can prove that actually the class S of factor is stable under multiplication and intersection. That means if you take G, H, two groups, then G times H, this is a group, and G intersects H, this is also a group, is contained in this tensor factor. Two corollaries. So, what is this? So, well, the main geometry is only just some specific situations. This is treat only the specific examples, but finally, using this main theorem, we finally obtain that kind of some general structure theory. Namely, the first one treats you can always find a nice representative from the 2-1 factor, right? This is one thing, and the second thing is using the first resource, you can always find a nice representative so that you can prove something more. The second one is particularly very general, general property which holds in the full generality. So this is, of course, this is far from the complete answer to this question, but still this is very interesting because this holds in the full generality, right? Okay, this is our main observation today. So, using our 25 minutes, I want to explain how to prove this main theorem. Just only the main idea. And also, I want to explain how to prove from the main theorem to the corollaries. This is also some ideas. All right. Okay. So, idea for the proof of the main theorem. And the main theorem. For this, recall that. Okay, M is a 2-1 factor. Recall that M is prime. M is prime if you have a tensor decomposition, then this implies M1 or M2 is trivial object of finite dimension. Here. If you have a tensor decomposition, 1 must be a trivial object. That means that M does not have a tensor decomposition essentially, right? And this obviously this notion is coming from the prime numbers. So recall that is prime. The natural number prime if your number is decomposed into 2 elements. Okay, say equal Rs implies S equal 1 or R equal 1, right? Okay, this is the definition, right? Obviously, this primeness is inspired from this prime numbers. So, but, well, in the number theory, there is another notion of primeness. So recall that P is prime if your first element, P Q equal Rs happens, then PQ equal Rs happens, then P divides R or P divides S from here to here. This is also equivalent to notion of primeness. And in the number theory, usually the first one is called irreducibility. The second one is called primeness. But for prime numbers, they are equivalent. So, using this, by inspiring this notion, here I introduce another kind of primeness as follows. This is actually written in my previous work. 2-1 factor, okay, 2-1 factor, M is, say, strongly prime. In that case, the second one looks stronger than the first one, although they are equivalent for prime numbers. Strongly prime. If you have tensor decomposition like this, tensor production like this, like this, and P, Q, all 2-1 factors. Okay, so and P, Q, all 2-1 factors. That must implies something division, right? P divides R or P divides S. In the algebra framework, it's natural to use inclusion instead of division. So we want to say M is contained in P or M is contained in Q. We want. But as I mentioned in the prime factors theory of Ozawa and Popper, every tensor decomposition determines up to unitary conjugacy and up to perturbation, right? T's power of M and N over 1 over T's always happens. So you have to accept this difference. So the correct notion should be there exists T with some decomposition with some fixed decomposition, and there is some unitary element such that you have M is contained in P or Q. Sorry. Your M is up to unitary conjugacy. Your M is contained in this P part or Q part. This decomposition implies this conclusion. This should be a corresponding notion of the primeness. So, okay, so one remark is that the name strongly prime is appropriate because strongly prime, say S prime for simplicity, this implies primeness. But converse is not. Indeed, you can show that the S prime directly implies fullness of 2-1 factor, right? But the other one, this can be non-full. So you can distinguish primeness and S primeness using the fullness. This one is by Daniel Hoff's argument. Okay. So, in that sense, the terminology strongly prime is okay. So, okay, this is the definition, and what important is to find example, because obviously this is a very strong notion. So, in general, it's very difficult to find example. But fortunately, thanks to the technical development in the deformation rigidity issue, you can find example. Actually, this was written in my previous work. For example, figure factor is satisfy this S primeness. Right? Always this is S prime. So you have examples. So then, what important is yes. So what important is how to use this S primes. Our key lemma is, actually this is not difficult to prove. Somehow good exercise. Prove that our S primeness implies our conditional star. Star already I erased, but well, this is I want for the main theorem. But you have only to prove the S primeness and S primeness, but I already proved some examples by using technologies of deformation rigidity theory. So that means thanks to key lemma and the technology from the deformation rigidity theory directly implies the conclusion that main theorem. This is the idea of the proof of the main theorem. But this is not, well, you need, of course, some argument. Well, but I omit this part. The fundamental idea is this strong primeness. So, and I forgot to mention that in the definition of strong primeness, S primeness, actually this is first suggested by Taka in 2013 when I was in a conference. Taka considered this condition and asked me whether or not Frege factor is S prime. But I and Taka couldn't solve this problem. But sometimes later I could solve this, so I wrote some. I wrote this in some of my paper. But anyway, at that time I and Taka both couldn't find nice applications of this S prime. But recently, actually last year or 2 years ago, I found that key lemma. So that I again started this work and finally found such a main theorem and corollaries and so on. Okay, this is just a story. Yeah. Okay. Now I have almost 30 minutes. Finally, I want to mention how to deduce from the main theorem to corollaries. This part, again, I have to use the strong dichotomy theory from the deformation rigidity theory. But okay, for any strong factor n, we will show the fundamental group coincide with some free product. Any to one factor, and you can find some free product to one factor whose fundamental group equal to f of n. Right? And this is actually, obviously, this is implies corollary A. Because the free product always satisfies condition star. So you can always find a representative of to one factor with condition star. Right? The idea is the use of two very strong theorems. One is from the free probability theory, the other is from the deformation rigidity theory. So theorem, Dykman address. Let n to a factor of infinity main cop something. Then you have intersection of this the fundamental group. Intersection of the fundamental group is contained in this infinite free product. This is one inclusion. Okay. Well, this is in the tensor product situation, this kind of one inclusion is very trivially holds, but in the free product situation, to obtain one inclusion is highly non-trivial. But this was done by, from the free probability theory. So this is one side is okay. For the other side, I will use Yuan Peterson Popper, this paper. converse holds if the inverse. This holds if each Bn satisfies some rigidity assumption. Such as relative property T. Relative property T with, for example, regular subalgebra or something like that. You need some strong assumptions. Okay? For example, property T itself is enough, for example. But we cannot assume this kind of property T for such a general situation, right? So, but, okay, this was formulated by Iona, Peterson, Popper, but later, so we can find a kind of another, way of obtaining rigidity assumption. This is so-called spectral gap rigidity. This is also by Sorin himself. Spectral gap rigidity. Spectral gap rigidity is enough. So-called spectral gap rigidity is okay. A typical example is that each Bn, sorry, that is Mn, sorry. Each Mn is non-amenable and non-prime. Non-amenable, well, you always need this assumption because amenability is very on the contrary to the rigidity phenomenon. So you always have to assume non-amenability. Then the essential assumption is non-prime. Non-prime means this Mn has a tensor decomposition of non-trivial tensor decomposition. Then you can apply this inverse direction. Well, actually, to apply that argument in that framework, you need some more effort. But because spectral gap argument works only for free product of finitely many components. But this technical problem was already solved by Udaye and Ueda's paper. So infinite case is also okay. So now combined with these two, we have for A, okay, M and N, two more factors. The fundamental group coincides with this, right? We put all of this Mn as M to the N, right? One inclusion always holds true if each one is 2 factor. The other direction, we can use this non-primeness assumption. Oh, in that case, non-amenable is necessary. Right? So you always have this inclusion at first. Then, now I apply our main short. That is, if N is our condition star and the fundamental group is trivial. You can find actually such example. Then, this left-hand side, this at first decomposed in Fm times Fn. This is by condition star. This is by our condition star. N is specific and M is general, right? And finally, you can remove this F of N because this is trivial, right? So you finally obtain this equal under the assumption that M and N are non-amenable to our factors and N satisfied condition star with this condition. This always holds. This and this, right? Okay, this is, well, essentially main observation actually. Well, so now you this actually obviously implies that, well, f of m is equal to some free product. This is we want. This we want it, so that the corollary holds, right? This is the first corollary. And for the second corollary shows the class S of factor. Oh, sorry, I have to mention that this n is exist. N is, for example, free group factor with some gamma. Gamma is G cross S to G. If you put the free product of these two guys, then from Iona Peterson Popper's paper, this always satisfies the fundamental group trivial. And also, this satisfies condition star. This is because this is a free product, so you can apply our main theorem today, right? So you can always find such an n. So this is okay, right? So actually, I have 5 minutes, but well, this directly implies the multiplication part. Okay, let me write something. So, to prove corollary B for, well, but this is almost trivial. If G, you have C, this is f of n, this is f of n by definition. But you can assume that this is with star. Right? One is with star. Actually, the other can be also with star. So that this coincides with, right? And this is G times H. This is realized as a fundamental group of the M tensor. This is inside S of factor. Okay, this is the case of the multiplication. So, and also for the intersection, you can actually apply some very similar argument to that one. I mean, because this theorem and this theorem both hold for the intersection. So you can apply actually very similar way of proving this corollary B, so that you can conclude this. Okay, so I have 2 minutes, but I stop here. Thank you very much.
Go for the line.